Hello everyone, welcome to this channel where we will have a brand new series called Zero to Hero in IGCSE Computer Science. And in this video, what we're going to do is that we're going to revise the entire chapter 1 of IGCSE Computer Science called Data Representation. Let's jump straight into it. The first topic that we're going to revise today is called the number system. Alright, and the first system that we're going to go through is called the binary system. And binary system, the reason that we are learning it is because any form of information here, such as text, images, music, they need to be converted into a binary format so that it can be eventually processed by a computer, which means binary is the only language which a computer can speak in. And this is because computer contains millions and millions of tiny switches which can be turned on and off. So let me explain. Therefore, binary system is chosen as the way for a computer to represent any sort of data, in which when we turn on the switch, it means the value 1. And when we turn off the switch, it represents the value 0. Therefore, in binary system, there are only two possible values, 0 and 1. But think about it. The basic system that we use in our day-to-day life, for instance, we have 365, the number of days in a year. The number system that we are used to is called the Denary system, in which we know that this value is 365 by multiplying the digit value, let's say 3, with the place value 100. So we will do 3 multiplied by 100, 6 multiplied by 10, 5 multiplied by 1, and eventually we got the value 365. And yes, this is how we understand numbers in our day-to-day life. But as I mentioned, computer cannot understand Denary. The only language that they can speak in is binary. And therefore, in this video, we are going to learn how to convert binary to Denary and Denary to binary so that we can input numbers into the computer, so that we can transmit data to the computer using the language that they can understand. So let us start with the conversion of binary to Denary, 1011. So how do we convert this binary value into a Denary value that we can understand? And it is very similar to how we understand Denary system. Like what I mentioned, how we obtain the Denary, how we understand Denary system is by multiplying the place value with the digit value. The only difference here in binary system is that the place value of each position in binary system is different. Instead of the rightmost digit would have a value of 1, which is similar to Denary system. But the second rightmost, instead of the value tens, we have 2, which is 2 power of 1, followed by 2 power of 2, which is 4, and 2 power of 3, which is 8, so on and so forth. We just increment the power. And to obtain the Denary value of this binary, all we have to do is to multiply the place value with the digit value. So will be 1 multiplied by 8 plus 0 multiplied by 4, alright, plus 1 multiplied by 2 plus 1 multiplied by 1. And we'll have the answer of 11. So let us check if that's the correct answer. Yes. So we have the value of 11. And the way we do this is just by multiplying the digit value with the place value. The things that you have to take note here is what is the place value of the first position, the second position, the third position, and so on and so forth. Each value is multiplied by 2 in order to reach the next value. And to do it the other way around, how do we convert a Denary value, the value that we all understand, into binary, a language that computer can understand? So we have the value 39 here. And the way that we can get the binary value of this Denary value is that we will keep dividing it by 2, keep dividing it by 2, and use the remainder of the division to get our answer. So for instance, 39, when we divide by 2, we got 19 with as the quotient and 1 as the remainder. And if we were to continue to do this, 19 divided by 2, we got 9, remainder of 1, 4, remainder of 1, 2, remainder of 0, 1, remainder of 0, and last but not least, 1 divided by 2, we got 0 as the quotient and 1 as the remainder. To obtain the answer, all we have to do is to read the remainder column from bottom to up. And by reading it from bottom to up, we can construct our answer 100, 111. And this value here will be the binary value of the number 39. So let's check the answer. Yes, 100, 111. And that's how you convert binary to denary and vice versa. Next up, the other number system that we computer scientists will care about is called the hexadecimal system. And it is a base 16 system. In binary, we know that there are only two unique values, 0 and 1. Therefore, it is a base 2 system. And in denary, we have the value from 0 to 9, as you can see in this table, in which it is a base 10 system because it has 10 unique values. Binary only 0 and 1. And in hexadecimal, there are 16 values. First up, from 0 to 9, and it's not followed by 10, but instead it's followed by character, which is A to F. So in hexadecimal, the unique values are ranging from 0 to the character F, in which A is equal to, we have a table here which map binaries into hexadecimal and denary. As you can see, A in hexadecimal is 10 in denary, and B to 11, so on and so forth. This table is important. You might need to construct it during your exam to do the following question, which is the conversion of binary to hexadecimal and hexadecimal back into binary. So imagine this is the binary value that we have, 1011, 1110, 0001. And the way we can construct the hexadecimal of this binary, the first step is to split the binaries into a chunk of 4. Alright, so we have 3 chunks here, first chunk, second chunk, and third chunk. And using the table that I introduced just now, we can map this chunk of binaries into their respective hexadecimal value. So let's find 0001. If we look at the table, it is 1 in hexadecimal. It's 1 in hexadecimal, so I just put 1 here. And 1110, we have the value of E. So we'll put the value E here. Sorry for the bad handwriting. And last but not least, 1011, we have the value of B. So the full answer of this binary is BE1. So that's how we got our final answer. Easy, right? That's why one catch for you is that in the exam, you will have to construct this table by yourself. It won't be given. So it's important for us to construct this table by ourselves, right? So let's look into the other question, in which it's the same type of question, but here we have 14 digits in binary instead of 12, so that when we split this binary into chunk, we got 4 chunks, all right? And however, the leftmost chunk, as you can see, only has 2 digits, but we cannot find 10 in our table here. So what do? So in this scenario, what you have to do is that you can just add the leading zeros to the value so that you can refer this value back to the table. So by mapping these binaries into the table, we get the value of 2, 1, F, D. Feel free to check out the table to see if there's any mistake, right? So the final answer of it is 21FD in hexadecimal. So let us do another question. This time is the other way around, in which we convert the hexadecimal value back to binary. So I guess you might have already know how to do this. Again, we map those values back into their respective binary value, which means we are referring from the right column to the left column. So the value f, we have 4 ones, all right? The value 9, we have 1001, as you can see here, all right? 3, we have the value 0011, and 5, we have the value 0101. And all you have to do is just concatenate all the string together to form our final answer here. So that's how you can convert hexadecimal to binary. In my opinion, they are the easiest question that you can see in the exam, all right? So next up, the last two conversions that we need to do in this subject is to convert hexadecimal. Instead of to binary, we are going to convert it into denary and vice versa. So the method to do this is very similar to how we convert binary to denary. If you remember, the way we convert binary to denary is that we multiply the digit value to the digit value here to the place value here. All right? Okay? So in hexadecimal, the only difference is the place value. So the rightmost digit place value is still 1, but the next value, instead of 10, instead of 2, it is now 16. Remember, hexadecimal is a base 16 value. So we got 16 power of 1, we got 16, and followed by 256. It's gotten it from when we multiply 16 2 times, 16 to the power of 2. And again, now we can do the basic thing. But before that, we have to remember that in hexadecimal, there are some characters. So before we do our conversion, we do need to convert this character into value. For instance, A, we need to convert it into the value 10. So we can just do the basic stuff by multiplying the place value with the digits value, and we'll have gotten our answer here. Okay? Feel free to try it yourself. So next up, we're going to convert denary into hexadecimal. And the way we do this is very similar to how we convert denary to binary. If you remember, the way we convert the value 5 to binary is that we keep dividing it by 2. We have the remainder. We read the remainder from bottom up. Okay? So we have an example here. How do we convert the value 2004 into hexadecimal value? So instead of dividing the value by 2, which occurs in binary, we will divide it by 16. And if we were to do this, 2004, when we divide by 16, we got a value of 125 as our quotient and 4 as our remainder. So we just write the value back into our tables here. And let's continue to divide this 125 by 16. We'll get the value of 7th, remainder of 13. But remember, in hexadecimal, there is no value 13. 13 is represented by the character D, all right? And so on and so forth. We just divide 7 by 16. We got 0 as quotient and 7 as our remainder. To construct it, we read the remainder from bottom up, and we'll have the value of 7D4. So 13 is equivalent to the value D in hexadecimal. And that's it. That's all the conversion problems that we need to do. All right. Feel free to rewatch certain part or comment if you have any doubts on how to do this question. I will try my best to answer. And next up, having learned about the hexadecimal system, we are going to have a look on what are some of their usages in computer science. Why do we need them if we already have the binary system? And just look at this diagram. The binary value here, its corresponding hexadecimal value is this. Okay, I won't do the conversion part. You guys can try it yourself. And there are two reasons why they are used. The first one is, as you can see, hexadecimal is easier for us to visualize. All right, there are a lot of 1 and 0 here in binary. It will be difficult for programmers or computer scientists to read data in this way. Instead, it's easier for us to look at the hexadecimal value, which leads us to the second advantage of hexadecimal, which is it is more compact and shorter. Remember, 4 binary digits is equal to 1 hexadecimal value. So that reduces the length of the data by 4 times when we use hexadecimal. All right. So there are 4 usages of hexadecimal system. The first one is arrow codes, in which it tells the programmers where the arrow is located by putting up all this hexadecimal value. If you can see here, these are all hexadecimal value. So that's the first usage of hexadecimal. And the second usage of hexadecimal system is the MAC address. MAC address is basically an identifier for your device like laptop and smartphones. We'll go into that more in details in chapter 3. So as you can see, the MAC address of a device, feel free to check your own MAC address in your computer. They are also represented in hexadecimal. And the third usage of hexadecimal is the IP address, which is an address given to a device when it is connected to a network. So for instance, an IP address, it could be represented like that. See the red bracket in hexadecimal instead of in Denary. Okay. So the last usage of hexadecimal system is called the HTML color code. HTML is basically a language that programmers use to develop websites. It's not a programming language, but a markup language. So when you're making website, there are certain colors that you might want, and you would encode this into in hexadecimal. All right. So to summarize, because this is a very commonly asked exam question in IGCSE, therefore I use a mnemonic to help me memorize the 4 usages of hexadecimal system called the IME. So E stands for arrow codes, M stands for MAC address, I stand for IP address, last but not least, HTML color code. All right, having talked about hexadecimal system, let's move on to the addition of binary value. How does computer carry out addition? For instance, in our calculator apps, how do they multiply values and add values? So this is what we're going to look into the next 2 segments. So if you remember, how we carry out addition in Denary is that using this old school method here. Right, let me change another color for this background. So this is how we perform addition in Denary system. So 9 plus 1, we have the value 10. So 10 is our value, residual value, and 1 is our carried over. So we have, but in binary, it's a little bit different. If you remember, binary only have 2 unique values. So if we were to add 0 and 0, obviously we're going to get 0. 0 to plus 1, we're going to get 1. 1 plus 0, we're going to get 1 again. But if we were to do 1 plus 1, remember in binary, there's no value called 2. What it will do is that 1 plus 1 is equal to 1, 0. 1 plus 1 is equal to 1, 0. And how it works is that when we use 1 plus 1, we'll get 0 with a carried of 1. Because 1 is the maximum value in binary, and we just bring this carry down. That's how we get the value of 1, 0. If I were to add 1 plus 1 plus 1, I will get the value of 1, 1. It's not 11, it's called 1, 1, which is 1 plus 1 plus 1. If I were to do it here, we get 1 with the carry of 1. Okay, so that's how we add binary values. And let's try out an example here. How do we perform add in this example? So you can just go through with me. 1 plus 0, we got the value 1. 1 plus 1, we got the value of 1, 0. So our value here is 0 with a carry of 1. And move on, we have 1 plus 1, and we'll get 1, 0 again. So again, 0 with a carry of 1. 1 plus 1, 0 with a carry of 1. 1 plus 0 plus 0, we get a value of 1 with no carry. 1 plus 0, 1, 0 plus 1, 1. So that's all. That's how we convert this value into, that's how we add 2 binary numbers together. So that's the answer. And here I want to introduce another condition called the overflow condition. It might happen. So let's do this addition again. You can pause the video to try it yourself. 0 plus 0, we got 0. With the 1 plus 1, 1, 0. 1 plus 1 plus 1, 1 with carry of 1. Again, 1, carry of 1, 0, 1, 0, carry of 1, 1 plus 1, 1, carry of 1, 0, 1 plus 1, 0. See, we have generated 1 plus the ninth value, 1 plus nothing, we get the value of 1. So, when we add these two binary numbers together, we have generated an extra digits here, an extra 1 value here. Okay, what is the big deal of this, right? We care about this thing because when we are learning about hardwares, we know that the component that stores this value is called a register, and sometimes register might have a fixed size. What if the register that stores this value only can store 8 binary bits? If this happens, the extra bits that are generated here will be, oh, let me adjust it. The extra bit that's generated here will be lost. All right, if I were to do this all again, so this is the value that we'll get. So let me clear my drawing. Right? So the overflow condition is when a ninth bit is generated. This means that the value, the result of this summation has exceeded the value that a 8-bit binary numbers can store. And 8-bit binary numbers here, we have 8 ones here. If you check, the value of this is 255. But we know that when we add two numbers together, there is a chance for the result of this summation to exceed this value. And this is how the ninth bit is generated. This is called an overflow error, which means there is a risk that this extra bit generated here, the green color one, will be lost. The sum is too big to be stored using just 8 bits. Okay, so that's how we do addition and the overflow problems that we might face when we do this. In the IGCSE exam, they might give you just 2 binary numbers and ask if, okay, does overflow problem occur? You will have to answer this yes and give the reason of it. Why? Because the ninth bit has been generated. So having learned about how to add binary numbers, now we'll move on to how do we multiply and divide binary numbers. Think about it, it's necessary. There is a plus and divide functionality in your computer, right? So let's learn how do we do this. The method that we use to multiply and divide binary numbers is called binary shifting. Binary shifting. In essence, we are basically shifting the binary numbers. So let me give you an example here. So we have the binary value 111 here. And 111 in Denary, we can just multiply, use back the method that we learned, multiply the place value by the digits value, which we will get the value of 7 here. We'll get the value of 7. Okay, so let's try to shift this binary value 111 to the left, in which we will move each digit one place to the left. Alright, so when we move 111 to the left, we got 1110 instead. And I want you to observe the effect of this shifting. So from the table, we know that the Denary value is 8 plus 4 plus 2, in which we get 14. Alright, hopefully you are starting to observe some pattern here. So let me just move this binary one more places to the left. So one more places to the left, we will have 11100, and in Denary, this value is 16 plus 8 plus 4, in which we'll get the value of 28. Alright, can you observe a pattern here? When we shift the value of the binary to the left by 1 digit, the value of it is actually multiplied by 2. And if we were to shift it again, we'll multiply it by 2 again. So that's the pattern of it, is that when we shift the binary value 1 place to the left, we are multiplying by 2. If we were to shift it 2 places, we are multiplying by 4. 3 places, we're multiplying by 8. And by following this pattern, if we were to move n places to the right, we are multiplying the value by 2 to the power of n. Okay, if you can see here, when we move one place, we got the value 2, which is 2 power of 1. When we move 2 places, we got 2 to the power of 2, which is 4. When we move 3 places, we got 3 to the power of 3, which is 8. So this is how we multiply a binary value. We shift the binary value one place to the left. And to do division, we can do the exact same thing, but we just change the direction of the shifting. So for a CPU to divide a binary number, the numbers needs to be shifted to the right. So that, let me give you an example here. We have the binary value 101100. So the value here, the denary value of this binary is 32 plus 8 plus 4 will have the value of 44. So if I were to shift this value one places to the right, so I'm going to move this to this, here to here, here to here, here to here, here to here, and I'll get the result here. Alright, every digit being shifted to the right. And if I were to calculate this value in denary, it is 16 plus 4 plus 2, and we'll get the value of 22. And if I were to shift this one more places, I will get 1011, alright? And if I were to calculate the denary value of this, is 8 plus 2 plus 1, which will get 11. So from the value here, hopefully you can see the pattern. 44 to 22 is division of 2. 22 to 11 is again division of 2. So the same theory persists. 10110, if I were to shift one place to the right, is division by 2. 2, 4, 3 places divide by 8. And the formula, if I were to shift n places to the right, I'm actually dividing a value by 2 to the power of n. So, okay, so here they say that register contained within the CPU. Register is a component that stores all the bits that a computer needs. We'll talk more about it in chapter 3. And sometimes this register, the amount of data that can hold at one time is limited because the number of bits that they can store is limited. Therefore, the multiplying shifting effect can cause bits to be lost at one end of the integers and 0 added at the opposite end. This process is known as losing the most significant bit. So think about it, this is the value that we have, 10, imagine. This is the value that is stored in a register. If I were to shift this binary value one place to the left, so I would get 1011 0, 0, 0, 0, 0. But my register can only store 8 values. That means it can only keep the values here. So these values will be lost. And we call this scenario losing the most significant bit, which can have an effect on the result of the multiplication. So we have to be aware of this problem. So this is how we multiply and divide binary value. So let's move on to 2's complement, which is a number system that helps us to represent negative number. So a processor can also represent negative numbers such as -5, -100. And one of the methods that a processor can represent negative numbers is called the 2's complement. It's very similar to binary system, but with a slight twist. So before we start the conversion, learning the conversion, we have to take note of this, is that in 2's complement, if the starting digits starts with the value of 0, this means that it is a positive value. And if the leading bit is 1, this means that it is a negative value. For instance, let us have this value in 2's complement. Without having to calculate this, we know that this is a positive value because its leading bit is 0. And on the other hand, if I were to have a value like that, without calculating it, we know that this is a negative value because it has the leading bit of 1. So let us try to see how we convert this, which I believe this is a new syllabus in IGCSE computer science. It doesn't appear in a lot of passive papers. So do pay attention when you're learning this. So there are 4 steps that involve in converting this negative denary value into 2's complement. So first of all, we just have to convert this value number into positive. So negative 67, we just have to convert it into the value of 67. And step 2, we have to write the number in binary form. What is the binary number of 67? So just to revise, this is how we do this. We keep dividing it by 2 and we get the remainder. 33, we got the remainder of 1. Alright, so 33 divided by 2, we get 16 and remainder of 1. And do it again and again until we divide the number until the quotient here becomes 0. Okay, so 2 divided by 2, we got 1, 0 as the remainder. 1 divided by 2, quotient becomes 0 and 1. So our binary value should be 1, 0, 0, 0, 1, 1. So this is how we can do this. So one catch here is that if you were to do this, remember, if your binary value is 7 digits, remember to add the leading 0. This is very important for us to find the two complements of this denary value. Remember to add the leading 0 if your result is less than 8 bits. So having calculated these values, the next step is to invert each binary value, in which we change 1 into 0 and 0 into 1. So 0 to 1, so we got 1, 0, 1, 1, 1, 1, 0, 0. We are basically inverting the binary digits. And in step 4, by using the inverted value, we add this binary number by 1. And we'll have the result of 10111101. And that's the end of our calculation. We have gotten the 2's complement of negative 67. So this is our final result. Okay. So let's try to convert another value like 65. You can try it yourself, right? This is how we do this. The 4-step summary. We convert the value into positive. We obtain the binary number. We invert the digits. We plus 1, and eventually we get our final result. Okay, the 5 steps that we have. So let us try to do things the other way around. Let's try to convert this 2's complement value into a negative denary. So without having to calculate everything, you would have known that this value here is a negative value. Negative value. The reason is because the leading digits of this 2's complement is 1. And how we do this is very similar to how we convert binary to denary, with one catch, is that the place value of the last move value, instead of negative 128, is instead of 128, sorry, is negative 128. And which we can just multiply the digits value here with the place value and sum them all up together. Alright, so that's how it is done when we convert, and this is how we obtain the negative denary. Alright, so that's how we can represent negative value in binary into a complement, and how we can do things the other way around. Okay, so far we have learned how to convert different numbers into binary, into a value that computer can understand. But we know that computer can receive data not just in numbers, but also in other formats such as text, images, and sound. So the next topic that we have here is how do we represent text, sound, and images if the computer can only understand binary? How do we encode this information into a language into the only language the computer can understand? Let's start off. So that's how we will see all these components. Let's say in a game called Fortnite, we have images, text, and music. So let's start out with text. Here they say that every character that is input into a computer must be represented by binary code, which means every character that you are seeing now on YouTube, on your Google Word, such as A, B, C, D, they are represented by some mysterious, I would say, binary code, even including the space and punctuation that we type in. Therefore, it is important, they say, point number 2, that computers have a common set of characters that are recognized by a variety of system, which means given a binary like 10101000, the computer have to understand that this bunch of code represent a character, let's say A. Alright? So the method that we use to map binary into character is called the character sets, and the two character set that we'll learn is firstly is called the ASCII code, and the second one is called Unicode. So let us look at these images here. It is the ASCII code table in which you can see that each letter here is represented by certain binary. For instance, the binary 0110001 represent the character A. So now, so on and so forth. And by using this method, the computer can understand, okay, the character that we are typing is called A because it can read the binary in 0110001. Okay, so that's how computer can read text. This is called the ASCII code. The other methods, the other character sets that they are commonly used nowadays called the Unicode, and this is because the ASCII code is not enough. If you look here, we only have 8 bits here. Okay, we know that the number of representation 8 bits binary can have is there's a limit to it. It's only 225 characters, which means ASCII code can only adapt to 255 unique characters. But we know that as we will type different languages into our computer, such as French, Mandarin, we need more we need more digits. So that's why Unicode is invented. It uses 16 bits instead of 8 bits to represent character in its set, which enables over 65,000 over characters. And these characters can be the emoji that we use day to day. Okay, so the two ways that we learn here, which a computer uses to represent text, is called firstly the ASCII code and also the Unicode. So let's move on to sound. And they say here, sound can also be represented in binary. The voice that you are listening now, my volume, they can also be represented in binary. And the way they do it, for a computer to successfully process sound, the analog signal input has to be converted into a digital sound. Sound will be captured, for instance, it will be captured by a microphone here that I have, and a piece of software will then capture it and convert this sound into digital. Digital data means 0 and 1. And this recording, this is the first keyword that we'll look into, is called a sample. The voice that they record is called a sample. And how sampling is used to produce a clip. So these are the 3 steps. First of all, the amplitude. How loud my voice is first determined at set intervals. This gives an approximate representation of the sound wave, and each sample of the sound wave is then encoded, the keyword, as a series of binary digits. For instance, here we have a sound graph here, which record how loud the voice is at a particular time. So 1, 2, 3, 4, 5, 6. And each time interval, the amplitude will be quantified. So the range that is used in this graph is from 0 to 9. So we know that 0 and 9 can be encoded into binary. So that's how a computer can read sound. And this, in point number 2, they said that if we were to increase the number of possible value used, so instead of 0 to 9, if I were to increase this into 0 and 1000, which means I elongates the range, this will increase the accuracy of the sample sound because the range is bigger now. But everything comes at a cost. If I were to record, if I were to increase the range, this means that the number of bits used to represent this sound will have to be increased. So this is called the sampling resolution, in which it is the number of bits here. You have to remember this definition. The number of bits used to represent sound amplitude in digital sound recording, which also known as bit depth. Bit depth, that's the equivalent of sampling resolution. In other words, if you were to increase sampling resolution, you increase the accuracy of the sound, which means your sound will be of greater quality. So that's how sound is represented. And a recording software here is also capable of taking multiple samples every second. This is measured in hertz, where 1 hertz means 1 sample per second. All right, if I were to record my sound in, I want 3 samples per second, it would be 3 hertz. So here's another definition here called the sample rate, which is called the number of sound samples taken per second. All right, so that's all about sound. The 3 definitions that we have here is firstly the sample, second one, the sampling resolution. What is the number of bits used to represent the amplitude of my sound? All right. Third one is the sample rate. How many samples do I take per second? And here are the pros and cons of using a higher sampling rate or larger resolution, which is if I were to use more bits to represent the amplitude, of course, the size of it will be bigger, produce larger file size, but it will also have larger dynamic range, better sound quality, less distortion. And the drawbacks of it is larger file, it takes longer to download the file and requires greater processing power. And it is a very commonly asked question in the exam, so make sure you understand all this benefits and drawbacks so that you can evaluate accordingly in your exam. Okay, so next up, having talked about how computer represent text, how they represent sound, we'll move on to image. Every image that you see now, even the video that you are seeing now, is actually represented in something called a bitmap. A bitmap, which is literally a map of bits that forms a particular picture. Video is just a series of pictures, and when rendered to display like a computer monitor. An image is made up of 2-dimensional, the horizontal axis and the vertical axis. And each pixel is stored in the computer as a series of binary numbers. And here we have a very cute puppy. And this image is also represented in pixel. To simplify it, I draw a 5 to 5 pixel here. So they have 5 vertical bar and 5 horizontal bar. So this is a 5 to 5 image. Okay, so let us look at some of the image. So as I said, computers can only understand binary. So this means that each pixel here, they are actually just a bunch of binary value. They are just a binary value in which each binary value here represents one color. Okay, so here we have. So imagine that here I only use 2 digits, one bit to represent one pixel. This means that my image can only be black and white, because if I only have 1 digit, the value that I can have is either 0 or 1. It can be either 0 or 1. That means I can only have black and white, which means if this pixel is 0, has the value of 0, the computer will represent it in black color. However, if I were to increase the number of bits used in each pixel, let's see. If I were to increase it, so imagine if I use 2 bits in 1 pixel, I would have 4 possible values, 0, 0, 0, 1, 1, 0, 1, 1. And I can assign each code here into one unique color, color 1, color 2, color 3, color 4. Which means if the number of bits that I use to represent 1 pixel is 2 bits, I can have an image of in total 4 colors. So as you can see in this image, there are 4 colors here, 1, 2, 3, 4. So the number of bits used to represent each pixel is only 2 bits. And if I were to increase it to 3 bits, I would have 8 colors. And here I will introduce a new terminology, which is called the color depth. The color depth is the number of bits used to represent each color is called the color depth. So in this image here, if I were to use 3 bits to represent each color, my color depth will be equal to 3. So like what we just see, if my color depth is 1 bit, I would only have 2 colors. If I have 2 bits, I might have 4 colors, 3, 8. So what about 8 bits, right? We need a formula to calculate this. And the formula that we can use to calculate the number of colors we have is 2 to the power of number of bits. Alright, number of bits. If I have 2 bits here, I'll use 2 to the power of 2. As you can see, I would have 4 colors. However, in modern computers that we are using now, they usually have 24 bits color depths, which means they can produce over 16 million different colors. Alright, so that's how computer can produce a variety of colors. So that's image. And another term that can affect the quality of an image is called image resolution, which is the number of pixels that makes up an image. So try to look at this diagram from A to E. The rightmost image here, it has the least resolution, which means the number of pixels, number of boxes that form the image is the least. This is why it has the lowest quality. Alright. However, if you look at the leftmost images, it is the clearest because it have a higher image resolution, more pixels to represent that image. So this is the definition of image resolution, the number of pixels that make up an image. So another picture here. So again, they ask, what are the cons of using a high resolution image? What if I want to have a higher quality image? This is pretty common sense, which the first one is the increase of file size, because the more pixels that you have, the more binary bits that you will need to store. And greater the size, the longer it is to download the image. And then point number 3, a certain amount of reduction in resolution is possible before the loss of quality become noticeable, which we will touch more of this in data compression. So now we'll move on to how we measure the size of certain data in computer. How does computer measure how many gigabytes, kilobytes that a file has? So let him first learn some of the basic terminology of storage in computer science. The first one is called the bit, which is 0 and 1. So this is how computer stores data. It is the basic unit of all computing memory storage term, and it's either 0 or 1. And move on, we have the terminology of byte. It's the smallest unit of memory in a computer, which every 8 bits here, like you see here, is called 1 byte. 1 byte. So if I would have 0110110 stored in my computer will calculate this as 1 byte because it's equivalent to 8 bits. And another terminology that you have to remember is called the nibble, which is half a byte, 4 bits. All right. So that's the basic terminology. But we know that computer can store a lot of bits. Therefore, a better organization system is needed, which we will learn is called the IEC base 2 system of units, where 1 kilo is equal to 2 to the power of 10 bytes, which is equivalent to 1024 bytes. So by using this, we can name the bytes better. Instead of saying I have 1,048,500 bytes, I can just say the size of it is 1 megabyte. It's easier to visualize and also easier to pronounce it. All right. So let us try to convert this bytes into kibibyte, mebibyte, and gigabyte. The way we do this is very simple. First of all, if I were to convert bytes into kibibyte, we just have to divide this value by 1024. And the value that I have here will be the value in kibibyte. What if I want it to be mebibyte instead? All I can do is just to divide it again by 1024. We'll have get the value in mebibyte. If I want gigabyte, I'll get again divide by 1024. I would have 64 gigabyte. All right. So that's how we convert bytes into the different units that we have. And to do this another way around, as you might have already guessed, is that we just have to multiply instead of dividing it. Just multiply by 1024 and get the value. All right. So that's how we restored, how we convert gigabyte to the different units that we have here. Okay. So let's do some exercise which can help us to calculate how big a size an image is, and also audio. So let's start off with image. How do we calculate the size of image? So there's a formula here which is to calculate the size of an image, we just have to use the image resolution, pixels, and multiply it by the color depth. And the way we can derive this formula is very straightforward. So imagine that we have a 2 by 2 image here, and we have a color depth of 2. And as you can see here, the way we can calculate the size of this image is to first determine how many boxes there are. 1, 2, 3 boxes, which we can get it by multiplying the image resolution, 2 by 2, we have 4 boxes. And each boxes, we need to know how many bits are there in each pixel. And here we have 2. So the formula is image resolution by color depth. So we are basically calculating how many bits are there in this image. And we can just use 4 multiplied by 2, we'll get 8 bits. So as you can see, this is the image resolution, and this is the color depth. And the size of it would be 8 bits. Alright, 8 bits, which is 1 byte. So this image, the size of it is 1 byte. So let's move on to a real exam question, image resolution. Let's say I have an image of 2048 times 2048 with a color depth of 16. I can just use the formula, the image resolution multiplied by color size, and we'll have gotten the values, the size of it in bits. But note here, the question said, I want the size of this image in bytes. Therefore, one more step is needed here, which is we need to divide by 8 to obtain the storage size in byte. Okay, so that's how we get our answer. So that's how we calculate the size of an image. All right, it's pretty straightforward. And let's move on to how we calculate the size of a sound. And the way we calculate this is to use this formula. First is that we use the sample rate multiplied by the sample resolution and also the length of sample in second. So let's look at one example question. Imagine that this is the question. They say that this is a mono sound, and they give you some sample rate, sampling resolution, and length of this music in second. And they said they want the size of the audio in kibibyte. So let us try to use this formula. We'll have gotten 7 million bits, okay? But since the question says they want the answer in kibibyte, we need to first convert it to byte. And the way we do this is to divide the number of bits by 8 and got the bytes. And to convert bytes into kibibyte, we have to divide it by 1024. So this is how we got the final answer. It's 861 kibibyte. So that's for mono sound. Another question that they might ask is that they will say, here we have a stereo sound. So let's read the question. An audio CD has a sample rate of 4,000. Let's highlight the important details, all right? Sampling resolution of 16 bits. And the music sample uses 2 channels to record for stereo recording. Stereo recordings means if you were to bring your headphone, the left and right headphone will have a different voice. That's called stereo recording. And calculate the file size, they said, for a 16-minute recording. So that's a catch here. Remember the formula is sample rate multiplied by sampling resolution and multiplied by time. But the time should be in second. So therefore, we need to convert this length into second, which is 3,600 seconds. So here, the way we can do this is just to multiply everything together, all right, 44,000 and so on, to get the number of bits. But here's the catch here. Because this is a stereo sound, we need to multiply the value that we have here by 2. So we need to multiply the number of bits by 2. This is only needed for stereo. If it is a mono sound file, it is not needed. Okay? So that's how we just have to divide it by 8 to get the number of bytes. and eventually multiply by it to get the file size in MB. So that's about it for how we calculate file size in images and in sound. And let's move on to the last topic of this video, called data compression. So like what we know just now, or we see just now, if we want to have a very high quality image or sound, we need to increase the number of bits. We need to increase the color depth, the sampling resolution, which would result in an increase in size. And there is a way that we can compress all these files so that we can retain the information but losing some of the storage size. So let's see how we can do this, how we can compress the data, just like in this animation here. And like what I said, file size of images and sound can be very large. Therefore, we need to do something called the data compression. It is equivalent to the zip function in your computer, if you notice. So here are some of the benefits that to reduce the file size. The first thing is that we can reduce the streaming time, which means if this video size is smaller, it is easier for me to upload it to YouTube. And reduce time taken to upload and download media, reduce costs. Cost is very important. If you go to the market and try to look for a 128 gigabytes and 256 GB of hard disk, you will know that the price is very different. Therefore, by reducing the size, we can actually reduce the cost and save storage space, very straightforward. So there are two different types of data compression that can be carried out, especially for what we will learn in our syllabus. The first one is called the lossy file compression. Second one is called the lossless file compression. So let's start off with the lossy file compression. It is an algorithm that eliminates unnecessary data from the file. And one setback of it is that the original file, once you have compressed it, it cannot be reconstructed, all right? And some of the lossy file compression algorithm that we'll learn is the MPEG-3, the MPEG-4, MP4, and also the JPEG. Okay, so here are some of the details of MP3. It's a compression technology that reduces the size of a normal music size file by 90%. And the way that it does that is it removes sounds outside the human ear range, which means when we record a sound, there is certain sound that cannot be heard by us, but they take up some of the storage space. So this algorithm, they remove all the sounds that we cannot hear, and they eliminate, look at point number 2, the softer sound that we can't hear, all right? So that's MP3. So MP4 allows storage of multimedia file rather than sound. And the secret of how you compress file is that it removes certain pixels in the algorithm, in the video, without us noticing what is the difference. That's for video, and JPEG is for the image. It will reduce color shades that we cannot notice. So so this is how we reduce the file size of image and sound. So if you remember how we calculate, the formula to calculate the size of image is image resolution multiplied by color depth, which then will give us a size. Therefore, if today I ask you, how do we reduce the size of an image? There are literally only two methods. First of all, we reduce, let me use another color. We reduce the image resolution, or we reduce the color depth of the image. So that's how we can do this. This is, I believe is a past year exam question. They said, how does lossy file compression reduce the size of an image? So that's the two methods that you can use. Reduce the resolution, reduce the color depth. And let's move on to like the formula to calculate a sound, which is sample rate multiplied by sampling resolution multiplied by time. Alright, okay. So the way we can reduce the file size of a sound, again, is either we reduce the sample rate, or we reduce the sampling resolution, or we can even reduce the length of the video to reduce the size. Okay, so that's how all these things can be linked together. So having talked about lossy file compression, the way that I remember this type of file compression is that Instead of lossy, I call it lousy, because once the file size is being compressed, it cannot be reconstructed. It is very lousy. But here's another data compression method which is better than lossy compression, which is called the lossless file compression. As implied by the name, once you compress it, you won't lose any forms of data. It's lossless. You won't lose any. And what they say here, all the data from the original uncompressed file can be reconstructed. Once you compress it from, if let's say you have a file, you compress it, CF, compressed file, you can reconstruct it back to F. This is important because sometimes when we compress file, we don't want to lose out some information, important information, such as, let's say you are working on a very complex spreadsheet for your company, you don't want to lose certain data, okay? It's a compression algorithm that is designed so that none of the original details from the file is lost, okay? So one type of algorithm that do lossless file compression is called the run length encoding. So what it does is that it is used for a compression of numbers of different file formats. It reduces the size of a string of adjacent, that's the keyword, and identical data. All right. A repeated string is encoded into two values. Let me give you an example here. Say, let's say we have the data here. We have 5A's, 4B, 2C, 5D concatenated together. And they are just identical of each other and they are adjacent of each other. And how run length encoding would do is that, the file size here will be 16 bytes, assuming that each character is represented by 8 bits. But there's a way for us to further compress this file. So let's say we can actually encode, instead of encoding 5 character A here, we can encode number 5, the number 5, and with the digit, the number value that represented A. So this means that instead of us using 5 bytes here, 2 bytes here is enough to represent the same information. All right. So if I were to continue here, so let me clear my marking. So here we only need 8 bytes for each digit. So 1, 2, 3, 4, 5, 6, 7, 8. Instead of the 16 bytes that we have there. So we have reduced the file size by half of it without losing any important information. However, run length encoding is only useful when your data is very identical to each other, okay? So, and if you were to continue your studies in computer science, you would have learned many different file compression algorithms which are much more advanced and efficient. And here, we have finished the entire chapter 1 of data representation for IGCSE computer science. So we have talked about a lot of things such as number system, how we represent text, sound, and images in computer. And we also learned how to calculate file size. And last but not least, we end the video with data compression. And I hope that this video will help you to revise better, and hopefully you'll get a better result in your exam. So that's the end of this video. Thanks for watching. See you. Goodbye.